Find the centroid of the area of the semicircle passing through the point 9, 0, whose center is on the origin and the diameter lies along the y-axis. So the first thing we need to do here is make a sketch of the graph here to see what's going on. So it's a semicircle passing through 9, 0. So here's 9, 0. And the center's on the origin, so here's the center. And the diameter is along the y-axis. Right, so yeah, no trouble to draw that. Notice though, because there's just as much area above the x-axis, all of this stuff, as below the x-axis, then due to symmetry, we actually know what y bar is already, right? Y bar has to be 0 because everything would balance out just as much above as below. So y bar is 0, so we only need to find x bar. So here's our x bar template formula, I guess, for integral, using the integral here. But there's something different about this. First of all, let's look at the bottom. So according to the centroid formula, really the bottoms of these centroid integrals, these will always be areas. It'll be the area shaded of whatever graph or whatever region you're looking at. So in our case, this is a semicircle, so this is just the area of the full thing here. So y2 minus y1 is just the area, right? So this is just the area of the semicircle, which we already know what the area of a circle is, right? It's pi r squared. Therefore, the area of a semicircle is half of that, so half of pi r squared. Now, we also know the radius of this circle, right? Because this is a circle that extends out to 9, 0, right? We can see it as a point at 0, -9 and 0, 9. So therefore, the radius of this circle is actually 9, right? So we can put that in here. So half of pi, 9 squared, that's 81 pi over 2. So that is the bottom done. So a little bit different approach to this kind of centroid. We have to look at it that way because it's not easy to be able to evaluate this integral if we don't do it that way. So we need to first discover what the area is here before we can continue. Okay? So the next step, though, we can do the numerator here, right? But the trick here is actually getting our functions here. Now, because we're doing x bar, we're looking at elements dx. So dx is summed from 0 to 9, right? This rectangle here. And we can see our functions that we actually need to do. Our upper function is y2 equals the root of 81 minus x squared. Now, why is that the function? Well, consider the area, sorry, not the area, the equation of a circle. This is the equation of a circle here, right? It's x squared plus y squared equals the radius squared, right? So if we solve that for y, we get move the x squared to the other side, so we get r squared minus x squared, and then take the square root of that. Now notice though, when we take a square root, we actually can get a positive or minus here, right? So I'll just indicate that, right? We can get a plus or minus when we take the square root. Okay, now in this case, our r is actually, with r equals 9, right, we get y equals plus or minus, right, because when you take the square root again of some quantity, you can get a plus or minus. So 9 squared then is 81 minus x squared. So that's where our root 81 minus x squared comes from. So the only other thing is to use both the positive and negative here. So for the upper function, it's in the positive quadrant. Remember, the quadrants are these regions formed by the x and y axis. There's 4 of them. I've only shown 2 here on this graph. But in this quadrant, y is positive. In this quadrant, y is negative. So that's why we need the negative here. So those are your y2 and your y1 for your x bar in this case. So substituting those in, notice y2, here's y2 minus, now here's the tricky part, it's minus a minus, right? Or subtract a negative, I guess I should say. So subtracting a negative means we're adding them. So we actually get 2 root 81 minus x squared. Okay, and here's our area that we already found for the bottom part, that we had to do it this way in this case because we couldn't actually evaluate that integral in an easy way, so we actually had to do this, or at least recognize this part in the blue over here. So that's 81 pi over 2. So the integral of the top is actually not too bad an integral to figure out if we do some u substitution here. So if we let u equals 81 minus x squared, then of course the derivative du dx is negative 2x, which means that du equals negative 2x dx. Now we actually have all that, right? We have root of 81 minus x squared, so that will be root of u. That's u inside here. Then we have 2x, x times 2 dx. So that's almost there. So we actually very close to having du except for the negative, right? So instead of, in order to change that, I guess I'm going to stick the negative in here, right? So here's the negative sign going in front here because we need negative du, right? Not du. Or sorry, not a positive 2x dx, we need a negative 2x dx. So I just put in a negative here. Alright, so once you've done that though, once we replace everything in terms of u, we had to change those limits of integration here. So 0 to 9 can no longer be our limits of integration because that was for x. So 9 then becomes, well, whatever u is. U is equal to 81 take away x squared, so that's 81 take away 9 squared for our upper limit. And for our lower limit, it's 81 take away 0 squared, which is 81. So we put those limits in there, we get actually going, might seem a bit weird, we're going from a lower or a higher number, that is 81, to a lower number 0. But we can actually, and as you can see here, I've done the integral in terms of u, so that's u to the half. So u to the half, we'll integrate that now, and we'll drop the integral signs because we've integrated. That's u to the half, so half plus 1 is 3 over 2. Over 3 over 2, but remember I flip it again to make 2 over 3. Right, and it's just that, just to remind you of that again. If my result of integrating is u to the 3 over 2 over 3 over 2, then it's much easier to write that as 2/3 u to the power of 3 over 2. It's easier to work with that way. Okay, but I still have my negative sign here. So we could actually do this integral, we've done the integral, sorry, we could actually substitute here our limits of integration 81 and 0 with the negative sign, or it's actually something in calculus says that you can actually switch these limits of integration if you get rid of the negative sign here. So that's what I've done here, right? I've gotten rid of the negative sign, and to make it going from 0 to 81 this time rather than 81 to 0, and still 81 pi over 2 on the bottom there. So then I substitute in my new limits of integration from 0 to 81. So 81 raised to the 3 over 2, well, that's just the square root of 81, right, raised to the power of 3. So that's 9, right, square root of 81 is 9, raised to the 3 is actually 729, which I've written here, times 2 over 3. Notice again, as always, this term contributes nothing, it's just 0. So now we got 2/3 times 729 divided by 81 pi over 3. If you evaluate the top here, you get 486, and the bottom was 81 pi over 2. Rearrange that a little bit. I brought the 2 up to the top and multiplied according to fraction division rules. That's 972 over 81 pi, and this then is 12 over pi. Therefore, the centroid then is actually going to be right on the x-axis at a point of 12 over pi. Right? And just as a check, results in calculus have shown us that the centroid actually is any centroid in x, when we're dealing with semicircles like this, it's actually 4r over 3 pi. Right, and if there was a y bar, it would be still the same thing, 4r over 3 pi. So our radius was 9, and I think if you plug in 9 here, you will see that this indeed equals, it's 36 over 3, which is 12. That's 12 over pi. So that result is for every semicircle region, you can do 4r, which r is the radius, over 3 pi. Actually, it doesn't have to be semicircle, it could be quarter circle. But that's the known result, or a well-known result that we can use here. So x bar is 12 over pi. And like I said, that would be on the x-axis, because remember, y bar has to be 0, just to show the graph again. Y bar would have to be 0. So 12 over pi is somewhere on this line, and the centroid would be somewhere on that line. And yeah, so that is the centroid, right? It's at the x bar, 12 over pi, and at a y coordinate of 0.